Okay, in this video we're going to look at triple integrals. So triple integrals, now that hopefully if you've gone through double integrals, this is simply building up another iterate. As you know, the double integrals, we introduced the concept of these are iterated integrals. So if you can have two iterates, you can have three or n iterates. So it doesn't stop at triple integrals, it can go much further than that. However, we will limit ourselves to this final iterated integral, which is the triple integral. Similar to the double integral, the triple integral is computed almost the same way. The only thing is you have this additional integral. Let's start again with notation quickly. So you see there is a region, there's a solid D over which you are integrating some function f of x, y, z, and we say v here because it's a volume. It's dA in double integrals because the area over which you are integrating is two-dimensional, so it's an area. Here you have a three-dimensional region that you're integrating over, so it's a volume. So now when we practically do the integral, we will end up with a situation. What you need here is you need a range of values of x. Say for instance, let's make up some values a, b, y is c, d, and z is e, f. So here, and imagine if we did x first, y second, and z third for the sake of argument. So then we'd be talking a, b, c, d, and e, f. And we will be talking about f, x, y, z, and dx, dy, dz. Now generally when we go to, usually you'll not find integrals that have numerical limits. What you'll usually find is, like in double integrals, the first innermost integral has some variable limits as functions in fact, and then the second integral in this case can also have those. Only this the last iterate integral will have in fact numbers on it. So what you can expect to see, for instance, is you can have numbers here, for instance the last integral, and depending on the order, for instance, usually you'd find that usually we do z first. So you have z is a function of xy, so you can go from some function xy to u2 some function of xy, and then in the next one we do y next. So then you would of course have a function of x, in other words, as the limits here. So you would have some function, say h1 of x up to h2 of x, and that'll leave you with something that has only a function of x, and the final integral then with respect to x, which actually has numerical limits, as you see here. These a and b, we expect them to be numbers. So this is just to give you an idea of how you can structure your integrals and what to expect. As you'll see, it is similar to what you've done before. The new thing is this one here, this third integral, which happens to be a function of xy. Now, of course, if you do this instead of z, you had x here, then this would be a function of yz. Okay, and this could be function of z, for instance, if z is the last one, and so on. I think you get the idea. Right, in order to calculate this integral, the main thing you'll see here is the region B, which is bounded by the planes x equals 0, y equals 0, z equals 0, and x plus y plus z equals 1. The best thing I can tell you about these things is, without even drawing anything, you start by first looking at the function of z here, 1 minus x minus y, and then you look at what else you have on z is z equals 0. Now this tells you that when x and y are 0, z is going to be 1. So in other words, as that's the lowest, well, could be negative, of course, but you will see that the planes are x equals 0 and y equals 0. That means your range of values of x and y are mostly going to be starting at 0. However, what you will notice is that, in fact, x plus y plus z is similar to planes that you've seen before, as in that they are slanted like this on the three-dimensional axis. So it's some kind of plane like this. And then you have, of course, x equals 0, z equals 0, which are straightforward enough. So anyway, here we can see that there are two ranges of the values of z, and clearly if I would assume, and we can see from the diagram that z equals 0 is the lower plane. So your z is between 0 and 1 minus x minus y. Okay, the next step would be that you substitute so that would mean that we will end up with if I put z equal to 0 in here, it'll give me x plus y equals 1, which means y is 1 minus x, and y starts at 0. So clearly y equal to 0 and y 1 minus x, which is a negative slope. So in the xy plane, you're looking at this type of a line. So clearly y equals 0. Y equals 0 is here, and y equals, so we have, of course, that means that y is between 0 and 1 minus x. Okay, and that leaves us with the last one, which is x. And for that, we need to look at the intersection points here. What these intersection points are, this one is 0 here, clearly. This one is when when y equals 0, x equals 1. So therefore, we have this situation. So x is between 0 and 1. And now we're ready to integrate. So here, 0 to 1. Second integral would be 0 to 1 minus x. And of course, the innermost integral would be 0 to 1 minus x minus y. And the function, of course, is z. So we're doing dz first, dy, and dx. Okay, and these are very simple integrals to calculate. The first one will go to 0 to 1. So this will be simply 1 minus x minus y all squared dy dx. That will become 1/6 of the integral of 0 to 1, 1 minus x all cubed. And that will come to 1 over 24. You can check that. All right. So in this case, as you can see, what's going on is you have a paraboloid y equals x squared plus z squared, and y equals 4. So the since the paraboloid starts at 0, 0, it's got a vertex, and it's along the y-axis. This means that your y range of values could be this. However, if we follow procedure and the same steps as we did last time, what you would be doing is you would use this equation to look at what is z in this case, and it's going to be y minus x squared under the root, plus or minus. Now, of course, the negative one would be the bottom of the paraboloid, and the positive one would be the top. So your z range is from minus y minus x squared to the positive y minus x squared. So that's going to be a range of values of z. So that's done. That will mean we'll move on to possibly y. Now, on the y-axis, xy-axis, what you're looking at is a parabola. Okay, and of course, on the top, you have y equals 4. This is along x. So this, you can get this easily by putting z equal to 0. So that'll be in here, you put z equal to 0, and it gives you, because we're looking at it, where does it intersect the xy plane? What's in the xy plane? What's the picture you see? So that will give you y equals x squared. Okay, and we know y is equal to 4, so you get this, which means your y range, and clearly we can see that the parabola x squared is lower curve, and the higher curve is y equals 4. Okay, so y is between x squared and 4. That leaves us with the x. So the other thing you will notice here is the intersection points that we're looking for, and these intersection points here, the values of x. So when y is equal to 4, x is equal to plus or minus 2. So here's 2 and here's minus 2. So your x range is going to be minus 2 to plus 2. And so you're ready to integrate. X will be last, y would be in the middle, from x squared to 4. And of course this would be minus square root of y minus x squared to square root of y minus x squared. And of course what you're integrating is x squared plus z squared, dz first, dy second, dx third. The problem with this is, although this is absolutely correct, but the integration here is excruciatingly difficult. Okay, so here's an alternative that we can try. You might have noticed that the values of that we can clearly see that one easy range of values is y goes from x squared plus z squared to 4. Now in this case, if we were to apply this first, that means we would have some region, say D here, and if we were to integrate over the y range, it would be like this. It would be x squared plus z squared up to 4, and we're integrating, of course, x squared plus z squared dy first, and we'll say dA for the moment. Okay, now if we were to do this, what would happen is you'd end up with some region D here, which I'm deliberately leaving for the moment. We'll come to it because it'll become a double integral. But here, if I apply this, I'll end up with, in fact, 4 minus x squared minus z squared. Okay, and that will be multiplied by the square root of x squared plus z squared dA. Now that's a double integral. Now, one thing you should be able to hopefully see here, I hope, is that the reason I've brought this to a double integral is what's left is, in fact, we need to integrate over x and z. But the good thing is that we can actually use polar coordinates here. So if we were to use polar coordinates, it would mean that we would use x equals r cosine theta and z equals r sine theta, because if you treat it as a double integral. Now later on, when we do spherical coordinates, I'll show you another way to do this using spherical coordinates, but from the beginning, I mean. But for now, this is just using what we do know. So if x is r cos theta and z is r sine theta, we use that. It means that your x squared plus z squared will become r squared. We'll put y equal to 4, so that would give us where this intersects the, in other words, when y is equal to 4, then we're in the xz plane and we get a circle. And that circle is going to be, from that equation, 4 equals x squared plus z squared, which means radius, we're looking at a radius 2 here. So that means your r would be between 0 and 2, and of course it's a full circle, so your theta would be between 0 and 2 pi. So that means the integral will become 0 to 2 pi, and then 0 to 2, and the 4 minus x squared minus z squared will just become 4 minus r squared, and this one will become just r. Okay, and then we'll be doing r dr d theta. Okay, and that's a very easy integral to solve, in fact quite simple, and you see the power of the polar coordinates here as well, hopefully, and that will then boil down to 0 to 2 pi, and then the 4r squared minus r 4, if we take the two r's inside, so it's going to be 64 over 15 d theta, and that'll just become then 128 pi over 15 as our answer. So a rather difficult question, easier to set up the integral than to actually solve it. So as you can see, sometimes the most obvious method is not necessarily the best one. Okay, so this is another example, and in this one I'm looking at this one, so that gives you the connection between the double integral and the triple integral. Now here you see we've actually done this example before, but if you remember, it was using double integrals to calculate the volume of the tetrahedron. And in that case, as you see here, we integrated over this 2 minus x minus 2y, okay, and from x over 2 to 1 minus x over 2 and 0 to 1. And of course, the volume was 1/3. Now, as a triple integral, the way we would do this is essentially, we would say, well, our z range of values from the first expression is going to be z equals 0, and it goes up to 2 minus 2y minus x. So those would be your range of values of z. Your values of x, of course, values of y would still be the same. It would be between x over 2 and 1 minus x over 2, and your values of x would be between 0 and 1. Now, the interesting thing is, when you calculate the volume of this tetrahedron, what would happen is the integral would be 0 to 1, x over 2 to 1 minus x over 2, and of course 0 to 2 minus 2y minus x, and all you would be doing here is dz dy dx. Notice there is no function here. F of x, y, z is not here. So that means that the region that you're always integrating over is a volume, in fact. So that gives us basically, when you work it out, it actually turns out to be the same. In fact, because the first step will show you that. If I take the first integral, that's going to be 1 minus x over 2. and that integrates to just z, which is 2 minus 2y minus x, and then dy dx. Okay, and that'll again work out to be 1/3 as before. So you can see here the connection between double and triple integrals in calculating